Hey everyone, welcome back. Last time we introduced this concept of vector space, so I want to get straight back into there. So suppose V is a vector space, and I want to look inside this vector space now. So we'll say, and that capital W is a subset of capital V. So the idea that if you want to draw sort of a generic picture, you can draw V as this box right here, and then W is some blob sitting inside, right? So we've got this subset of a vector space. If you remember back to when we were discussing vector spaces, to be a vector space, 10 different conditions need to be met, right? There are 10 properties, or as we say, 10 vector space axioms. Now, if we think about the various axioms, right, I mean, I don't want to write them all down, but there was axiom 1 and 2. Those were closure properties. Axiom 3, if I remember correctly, was commutativity, right? So U plus V equals V plus W, V plus U. It doesn't matter what order you add vectors inside a vector space. Now, there was property 4. I'm not going to write them all down, but let's write one more. U plus V plus W equals U plus parentheses V plus W. Right, that was our associative property. Now, if you think about some of these properties here, for example, property 3, right? Axiom 3, it is automatically satisfied by all the vectors inside W, right? If U plus V equals V plus W for vectors, all possible vectors inside capital V, then in particular, if you have vectors inside W, right, the commutative property holds. Same thing with associativity. So in fact, there are a number of the properties, the axioms for vector spaces, that hold within subsets. And let me write them down, or I'm going to list them. So let's say, notice notice that axioms, so they are going to be, what is it, 3, 4, and 7 through 10 automatically hold in W. What we say, so we say that these properties are inherited by W. So the point is, if we know that the properties hold inside all of V, then they're going to hold within the restricted set W. And this leads to the following definition. The subset W of the vector space capital V is a subspace of W, of V, if W is a vector space is a vector space under the operations on capital V. So if we have some subset, capital W, of a vector space V, we will say that it's a subspace if it's a vector space in its own right. And this, right, this is important right here then. If we know that V is a subspace, if V is a vector space, and we have a subset, we don't need to check these axioms right here. To show that we've got a subspace then, what we'll need to do is check axioms 1, 2, 5, and 6. Those are the ones that we are not certain whether they're going to hold. 3, 4, 7 through 10 are going to automatically hold for any subset. So to be a subspace, to be a vector space in its own right, there are only 4 things that need to be checked. Now we'll do some examples in a few minutes, but I need some facts here. So let's call this a theorem. If V, or let's say let V be a vector space, U a vector, and what else do I need? Yeah, so a vector in V, and let's say R, some real number, so a scalar. I guess I shouldn't say some real number, because we do allow scalars to also be complex numbers. Usually for our purposes, the scalars will be real numbers, but it's okay if they're complex numbers also. So there's 4 pieces to this theorem. So part A, 0 times U equals 0. Now notice the 2 different uses of 0 here. Here I mean the scalar, the number 0. Here I mean the 0 vector. So 0 times U, that is a vector, and according to this theorem, it's the 0 vector. Part B, R times the 0 vector equals the 0 vector. Okay. These seem obvious, but I'm actually going to verify a couple of these properties here. Part C, minus 1 times the vector U equals minus U. Now, you might say, of course that's true. Well, think about what this means, though. This is a vector right here. Who is this vector? It's the vector that happens when you take the scalar minus 1 and multiply it by the vector U. And what are we getting? What we're getting is this vector right here, right? That's the additive inverse of the vector U. And then part D, if R times U equals the 0 vector, then R equals 0 or U equals 0. And notice the 2 different uses here, right? R equals the scalar 0 or U equals the vector 0. So I'm going to prove a couple of these parts, and I'll just leave the others as exercises. You can look in the book. I think some of them are in the book. So proof. So let's look at property A. 0 times U equals the 0 vector. So what do I need to do? Well, let's look at 0U. That is equal to 0 plus 0 times, right, 0 is 0 plus 0. And then one of the properties we have in vector spaces is the distributed property. This is 0U plus 0U. And so now we have this equation. 0U is equal to 0U plus 0U. I can subtract 0U from both sides. So this applies. That. So if I subtract 0U from both sides, what I get is 0 on the left-hand side equals 0U on the right-hand side. Right? And that's what we want to prove. Let's also do part C, and then I'll leave B and D as exercises. So part C says minus 1 times U equals minus U. So what I need to do is I need to look at U plus minus 1 times U. If by adding those together I get the 0 vector, then I can conclude that this vector is the additive inverse of U. So let's go like this. Minus 1 times U plus U is equal to, well, this is going to be minus 1 U plus 1 times U. And remember, that's axiom, I believe it's axiom 10, u is equal to 1 times u. Now we can apply the distributive property. This is minus 1 plus 1 times u. Minus 1 plus 1, of course, that's equal to 0. So now we have 0u. And by part A, we know that 0u is equal to the 0 vector. So what we've shown then is that this vector right here behaves exactly as the additive inverse for the vector u. Okay, so we're going to need these facts at a later time. Now, from what we were talking about just a few minutes ago, let me write this down, from our earlier discussion, if u, let's say, or not if u, if w is a subset of V, then to show that W is a subspace, then to show, all right, if we want to verify that it's a subspace, to show that W is a subspace, we only need to check axioms 1, 2, 5, and 6. Now, suppose W is not the empty set, so it contains at least one vector. And let's see, do we want to give it a name? Oh, no. At least one vector. And that 1 and 2 are satisfied. So what we're saying then, we've got a subset of V. It has at least one vector, and 1 and 2 are satisfied, which means that it's closed under vector addition and under scalar multiplication. All right, so let's just suppose that these properties are true. So if, let's say, let's call it little w. So if little w is in capital W, we have at least one vector inside capital W, so let's call it little w. So if little w is in capital W, then what? Oh, then so is minus 1 times W. Why is that? Because we said that axioms 1 and 2 hold. In particular, that means that we're closed under scalar multiplication. So if W is in there, then so is minus 1 times W, and that is minus W. So this implies that 0, which is W plus minus W, is in capital W as well. So what did we just show? We showed that if W has at least one vector and axioms 1 and 2 are satisfied, I said satisfies, I shouldn't say satisfied, 1 and 2 are satisfied, so if it's closed under multiplication, scalar multiplication and addition, then properties 5 and 6 automatically hold, right? We showed that we have an additive inverse, and we showed that the 0 vector is inside W. What we just proved, so let's write this down, we just proved, it's a theorem, but this is a theorem that's important enough we're going to give it its own name, so this is called the subspace test. So, suppose W is a non-empty subset of the vector space capital V. When I say non-empty, that means that it has at least one element in it, at least one vector. If W is closed under addition and scalar multiplication, oh, just about to run out of room here, but and so if it's closed under addition and scalar multiplication, then W is a subspace of V. So this gives a nice way to check that we've got a subspace. There's three things to do. Show that there's at least one element. It's got to be non-empty, so show that there's at least one element in the set V. Show that it's closed under addition. Show that it's closed under scalar multiplication. If you can accomplish those three things, then you can conclude that you've got a subspace. Now, I said just a second ago, this theorem is important enough to give it a name. We will use this lots and lots and lots of times. And what it says now, remember, the definition of subspace is that it's a vector space. Right? A subspace is a subset of a vector space that is a vector space on its own. And what this tells us is that verifying that we've got a subspace is much, much easier than checking all 10 axioms, right? To show that we've got a subspace, all we need to do is check that it's non-empty and that it's closed under multiplication and or scalar multiplication and addition. Right? Okay, so we're going to do some examples here. Well, okay, let's get this example out of the way. So, if V is any vector space, then the set consisting of just the zero vector is a subspace called, it's got a special name, so it's called the trivial subspace. And let's just verify this real quick. So what do we need to do? We need to show that it's non-empty. Well, we're saying right here that it's non-empty, right? It's got the zero vector in there. Is it closed under addition? So let's say note that zero vector is in the set consisting of just the zero vector, and so is non-empty. Okay, now we need to show that it's closed under addition, so I need to choose elements from here. Well, the only element I can choose is 0, so all we can do is 0 plus 0. So since 0 vector plus 0 vector equals 0 vector, we have closure under addition. The last thing I need to check closure under scalar multiplication. So also, by our previous theorem, R times 0 is equal to 0, and so this set is closed under scalar multiplication. So anytime if we have a vector space, we're guaranteed to have at least one subspace, namely the trivial subspace. It's not an interesting subspace, it's just got this just has the 0 vector in it. But clear. So now let's try some more interesting examples. So next example, let's say recall that M sub nn the set of n by n matrices is a vector space under the usual operations, adding two matrices and multiplying matrix by a scalar. Let's let D sub n be the set of diagonal matrices. So these will be the diagonal n by n matrices. So the set of diagonal n by n matrices. So note that the identity, I'll write it as I sub n, the n by n identity matrix, is in D sub n. The identity matrix is definitely a diagonal matrix. And so that means that D sub n is non-empty. There's at least one diagonal matrix in there. If A equals, so let's see, what will a diagonal matrix look like? It'll look like an A1, A2, dot, 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 down to AN, with zeros everywhere else. And I'm just going to put big zeros here in the corners to indicate zeros everywhere except off of the diagonal. And let's call it B, and that's going to be B1, B2, dot, 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 down the diagonal. We've got B's and zeros everywhere else. All right, so I'm choosing two vectors inside D sub n. Then A plus B equals, let's see, if we add these two matrices together, what we're going to get is AI plus BI along the diagonal and zero everywhere else. So I'll have an A1 plus B1, A2 plus B2, going down the diagonal AN plus BN, and zeros everywhere else. This is an n by n diagonal matrix also. In other words, if you take two matrices in Dn, two vectors in D sub n, and add them together, they lie, the result lies inside Dn. You can say, and so Dn is closed under addition. Also, if we do R times A, that's going to give us a diagonal matrix also. So this will be RA1, RA2, dot, 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 RAN, zeros off the diagonal. This is in Dn. And so, Dn is closed under scalar multiplication. And now we can write our conclusion. Dn has at least one object in it. It's closed under addition. It's closed under scalar multiplication. So by the subspace test, Dn is a subspace of M sub n n, right? The set of all, or the vector space consisting of all n by n matrices. Do a few more examples. This one shows up occasionally, so I just want to get it on paper here. So let's let F, often written as F parentheses minus infinity to infinity. I want this to be all the functions. So let this be the set of all functions of the form little f from R to R. So it's a huge, huge, huge set. There's lots and lots of functions out there whose domain is R and whose output is in R also. Now, it turns out that this set F is a vector space, and I don't want to go through all the details. So we'll just say one can check that capital F is a vector space. Well, when we say it's a vector space, that means we need to specify how to add vectors and how to do scalar multiplication. So now remember, in this case, the vectors are functions, right? They're these things right here. So this is a vector space under the operations. So what does it mean to add two functions f plus g of x equals f of x plus g of x, and scalar multiplication works like this: Rf of x equals R times f of x. So this is a huge set. For example, what vectors are out there that live inside this set? Typical vectors in F. Sine of x. There's a function whose domain is a set of real numbers and whose output real numbers. So sine of x, cosine of x, e to the x, polynomials like x squared plus 3x plus 2, all kinds of functions live inside this set right here. In fact, so I wrote this polynomial: all possible polynomials live inside F. So let's let P sub infinity be the set of all polynomials. There's definitely at least one polynomial in this set P infinity. In fact, there's an infinite number of polynomials. So we'll say clearly P sub infinity is non-empty. Let's see what happens if you take two polynomials and add them together. What do you get? You get a polynomial. So since the sum of two polynomials, and I want to say this. Let's say this a little better. So given P of x and Q of x in P sub infinity. Suppose we have a couple of polynomials. Then P of x plus Q of x is in P sub infinity. Add two polynomials together, the result is a polynomial. And R times P of x. If you take some polynomial, multiply by a constant, the result is a polynomial also. And R P of x is in P infinity. By the subspace test. By the subspace test, P sub infinity is a vector space. Why is that? Because it's a subspace of a known vector space. So P infinity is a subspace of capital F. You can do the same thing here. So a similar argument shows that P sub n, remember this was the set of all polynomials of degree less than or equal to n. So this shows that P sub n is a subspace of F. And so that gives an alternate proof actually that P sub n is a vector space, right? Last time what we did is we went through and checked all 10 axioms for this. It took a little while. Now that we have this subspace test, we can do it very quickly. couple more, another fact that we need here. If, let's say, U and W are subspaces of V, then note that, okay, they're both vector spaces, which means that they have to contain the 0 vector. So then note that 0 is an element of U, and 0 is an element of W. So 0 is an element. Sorry, I just reverted to Math 248 notation, even though some of you have not used that. So I need to be careful here. Note that 0 is in U and in W. Maybe some of you, I'm sure, have seen that notation right there. That symbol right there means element of, and I started using that accidentally. You're not expected to know Math 248, so I'm not going to require that you use that. So it follows that 0 is in U intersect W, and so U intersect W is non-empty. Now, I hope you've seen this symbol before. This intersection, this is the set that is red, intersect, so we have U intersect W. It's the set of all elements that are in common, that lie in the overlap. Right, so the picture, if I've got U here and I've got W here, this shaded region right here, that's the intersection. It's the overlap. Now, if, let's say, let's use X and Y. So if X and Y are in U intersect W, so I'm choosing a couple of vectors inside the intersection, then X plus Y is in U. Why is that? Well, if X and Y are in the overlap, that means that they live in U. U is closed under addition, so X plus Y has to live in U. Same thing, same reasoning, and X plus Y is in V. So let's say similarly, if I look at R times X, so let's see. So similarly, R times X, if X lives in the intersection, then X lives in U. U is closed under scalar multiplication. That means that Rx is in U, and it's in, sorry, I used V here. That should be a W right there, and in W. So, U intersect W is closed under scalar multiplication and addition. By the subspace test, if we start off with two subspaces, the intersection is a subspace. And I'm going to write that as a theorem, and I'm going to say it a little bit more generally. If, let's say W1, W2, up through Wn are subspaces of some vector space V, then the intersection W1 intersect W2 intersect ... Wn is a subspace of V. So if you have a bunch of subspaces, the common overlap of those subspaces is a subspace, right? So your picture, I'll do it for 4 here, so there's the common overlap of my 4 sets. The intersection of subspaces is a subspace. So let's look at some more examples now. The next one, in P sub 3, so remember this is the set or the vector space consisting of all polynomials of degree less than or equal to 3. So in P sub 3, let's let W be the set of all polynomials of the form 1 plus ax plus bx squared. So let's take all possible polynomials that look like this. So for example, 1 plus 1x plus 1x squared. There's one polynomial in there. 1 plus 2x plus 4x squared. There's an infinite number of possibilities. So now note that, for example, okay, so let's say p of x equals 1 plus x squared, and q of x equal to 1 plus 2x plus 3x squared. Both of these are elements of P3. So these are vectors in P3, but what happens if we add them? P of x plus q of x, well, that's going to be 2 plus 3x plus 4x squared. This is not in P3. Why not? Well, because the vectors that are, sorry, not in P3, in W. Oh, sorry. Is not in W. Why is that? Well, the vectors in W have to look like this. They have to start with a 1. What do we have here? We have a polynomial, but it starts with a 2. So conclusion, W is not a subspace of P3. Why is that? Well, it's not closed under addition. Here's another example. Let's just do a few more examples. The idea of subspace and using the subspace test is very important. We're going to need this and be able to use this on a very regular basis. And it's one of these concepts that's a little more abstract. It takes a while to sink in. Why do we care about subspaces? We'll see as we go on. The first thing we need to be able to do is to decide, to check, to verify. Are we looking at a subspace or are we not? So let's see, in R2, let W be the set of all ordered pairs, x comma y, such that x is equal to 0 or y is equal to 0. So I'm writing this as a set. Now what is this? So let's draw the picture. So here's R2, right? It's the plane. And we're looking at all ordered pairs where the first coordinate or the second coordinate is equal to 0. If the first coordinate is equal to 0, that means that you're living on the y-axis. If the second coordinate is 0, if y is equal to 0, then you're living on the x-axis. So this set right here consists of the x-axis combined with the y-axis. Now note that 1, 0 and 0, 1 are in capital W. All right, so 1, 0 is right there. 0, 1's right there, but 1, 0 plus 0, 1, that's equal to 1, 1 is not. in W, right? 1, 1 is off of both the x and the y-axis. What does that tell us? It tells us that this set is not closed under addition. So W is not a subspace of R2. Another example, let's let A be an M by N matrix and let W be the set of all x in Rn such that A times x equals the zero vector. So you can describe this set W in words. W is the set of all solutions to the homogeneous system. Okay, so let's say that W is the set of solutions to the homogeneous system. The homogeneous parts is important here. If so remember, a homogeneous system always has the trivial solution. So 0 is in W. That tells us that there's at least one object, one element in W. If x and y are in W, then if I look at A times x plus y, the distributive property tells us this is AX plus AY. We know that AX is equal to 0 because x is in W, and same with AY. So that's equal to 0. Also, I'll say and A times Rx, that's equal to R times AX. AX is 0, so we get R times 0. And by the theorem that we looked at earlier today, this is equal to 0. So Rx is also a solution to the homogeneous system. What did we just prove? All right, so we just proved, I know this is an example, but it's an important example, and it's important enough that we're going to write this down as a theorem. So we just proved, let's say theorem, the set of solutions to the homogeneous system AX equals 0 is a subspace of Rn. Right, so that'll be important to know. That leads us to this definition. So if T from Rn to Rm is a linear transformation, then the set of all x such that T of x equals the 0 vector. This has a name, so this is called, so this is the kernel, Kernel, of T. Every time you have a linear transformation from Rn to Rm, there is this set called the kernel of T. And by exactly the same reasoning that we had in our last example, or our last theorem here, so by the same reasoning as above, the kernel of T is a subspace of the domain, so of Rn. Right? So here's an important way to find subspaces. Every time you have a linear transformation from Rn to Rm, there is a subspace. It's called the kernel. And I want to finish off with a couple of final facts. Let's just write this as examples. So the subspaces of R2, who are they? How is it possible to be a subspace of R2? Well, first of all, R2 is a subspace of itself, so R2. Lines through the origin are subspaces, and then the origin itself. So, subspaces of R2, R2 lines through the origin, and the trivial subspace. We can bump this up one dimension, and that's how we'll finish off. So subspaces of R3, well, R3 is a subspace of R3. Planes through the origin, lines through the origin, and then the trivial subspace. You should go through and verify these, or some of these, right? Check using the subspace test that if you have a line through the origin, that the resulting set is a subspace. You should check that if you have a line or a plane through the origin, the resulting subspace, or the resulting set, is a subspace of R3. All right, that's a good place to stop. We'll see you next time.